Welcome back, everybody, to the final session of the workshop. We're now going to switch gears a little bit and talk about delegation, algorithmic delegation in particular. Our first talk will be by Shaddin Dughmi. Shaddin, take it away.
Thank you. So I'm going to talk about delegating stochastic combinatorial optimization problems. So here's the setting informally. You're a principal, you want to solve an optimization problem, but there's uncertainty about your data. And you also don't have the expertise to solve the problem, so you're going to delegate it to an agent, and the agent will collect data, we say probe the data, and then give you some information about how to solve the problem. Right? The key point here is that the principal and the agent may have different incentives about what solutions they prefer. And also, collecting the data may be either constrained or costly. We'll talk about different models there. So I'm going to mention this is different than a lot of the principal-agent hidden action models you've seen before. In particular, the principal is the one who acts here. The agent collects information, suggests perhaps solutions to the principal, and then the principal chooses. That's not the only difference.
So you need to stand near that mic? Oh, this way. As you
Yeah. Yeah, let me do this. Hopefully everybody followed so far, at least. Okay. Yeah. All right. So that's not the only difference, but that's one of them. Okay. You'll see more differences later. Okay. So let's look at an example. That's kind of a toy example to illustrate the idea. Let's say you're a mayor of a city and you want to design a public transportation network. There's a rail network and a bus network you need to design. Maybe there's 5 designs for one, 4 designs for the other. You must pick one of each. Okay? So you could delegate this to a contractor who'll collect data and explore some of the designs and suggest them to you. But maybe that contractor has limited time. Maybe it can explore 4 designs total, maybe 2 bus networks and 2 rail networks, and they'll strategically choose which to explore, right? Or maybe there's a soft constraint where exploring each design incurs a cost that you know. Okay? So the contractor may have different interests for various reasons. I listed a couple that I made up here, but there may be others, right? And the question is, how can you, as the mayor, incentivize the contractor to explore and suggest designs that you prefer? So let me talk about our results at a high level before getting into the formal details of the model. So what we have here is a principal who faces a stochastic combinatorial optimization problem. It's a problem that if he had the expertise, he might solve by himself, or he may delegate it to an agent who has arbitrarily different preferences. And what we're going to study is the loss due to delegation, which we're going to call the delegation gap. So the high-level message of this the 2 papers I'm going to mention is as follows. So designing good mechanisms with a good delegation gap reduces to familiar tools from stochastic probing and stochastic optimization. And these are profit inequalities, generalized Pandora's box problems, and the notion of adaptivity gap. So those notions will pop up in my results. Any questions? So let me now define the model a little more formally. You have a finite set of elements. You have a downwards closed family of feasible subsets of the elements. I'm going to call that capital F. The elements are E. And then the principal has a stochastic value for each element, a priori unknown, drawn from a known prior. Okay? And this stochastic value x sub e for element E may be learned by probing the element. Possibly there's a constraint on how many elements you may probe, or which set of elements you may probe, or there may be costs associated with probing. So if you, as the principal, have the expertise necessary to go explore the data and solve the problem, what you do is you'd run what we call a probing algorithm, or a stochastic probing algorithm, if you've seen that literature. Here you adaptively probe some subset of the elements. Let's call that capital P. learn their values to you, x sub e. And again, your probing may be constrained, or you may have incurred cost in doing this. And then you select a subset of the elements that you probed, a subset of P, that should be feasible. It should be in this set system F, and will maximize your utility X of S. I'm assuming utility is additive across elements here. Okay? So the optimal algorithm of this form obviously optimally trades off your utility for the solution minus the probing costs, or subject to the probing constraints. Any questions on this undelegated model? Yes?
Just to be clear, if you don't probe something, you're not allowed to select.
Yes, so that's what I'm going to assume here. Yeah. Other questions? Okay, so we're going to assume that the principal doesn't have the expertise to solve the problem, or for whatever reason, they just want someone else to solve it. So he delegates to an agent. That's our expert. And the agent also has a stochastic per element utility. I'm going to call it y sub e here. In general, it may be different than the principals. And similarly, the agent may probe the elements. And for each time he probes an element, he learns his own utility and the principal's utility. He learns x sub e and y sub e, right? After he does this data exploration, he sends a signal to the principal, who then interprets the signal to select a solution. Or the principal may say, I don't like the information you gave me, I quit the game. And everybody gets utility 0 in that case. So there's some important modeling assumptions I'm going to mention. The first one is that the principal observes his utility for the solution he selects. So when he selects a solution, he sees how good it is, right? And there's a couple of different ways to think about it. Either one way to interpret this is that the agent, when he, let's say, proposes a solution or suggests a solution, provides verifiable information, provides a plan on how to implement it, and that makes clear the principal's utilities, right? Another way to think about it is that the principal gets to experience the utility of the solution through experience, and then gets to punish the agent accordingly by saying, hey, you didn't live up to your end of this contract, let's say, right? I like the first interpretation personally, and that's the one that's in the literature, the prior literature. Right? Agent provides verifiable information about a solution they select, they suggest. And what this implies is that the principal can stipulate and enforce requirements on the quality of the solution that they end up adopting, right? So they can say, I'm only going to accept plans, transit plans that guarantee that it takes this much time to travel from this borough to this other borough, right? So that's the kind of requirements that the principal can stipulate for any solution, right? And one way to interpret this is that the agent can't really lie about any solutions they suggest. They can only omit information about solutions that may be possible that they're not going to reveal to the principal. Okay? Yes?
Just to clarify about not lying, does this include things like the agent being able to say, here's something I did not check, and then they can't lie about this? Or is it just that they can't lie about properties of the solutions they're proposing?
They can't lie about the solution that ends up being adopted at equilibrium. Yeah. There may be other solutions that don't end up being adopted, and the principal will be none the wiser about how good those are. Yes?
I see. So X of subset of P is not, can't import things about X of subset of P in general.
No.
The particular subset of P is X.
Correct. The principal only learns his utilities for the set he ends up adopting. There may be other sets that are better or worse. He has no way of knowing other than the information from the prior.
Are we assuming that this learning of utilities comes before any payments to the
Correct. Correct. So typically, in the policies I'm going to present, the principal is going to say enforce requirements on X of S, and if this requirement is not satisfied, they quit the game and everybody gets 0. And that's fairly common assumption in delegation literature. Two other assumptions I'm going to make are pretty standard. I'm going to assume the elements are independent. That's, an assumption, obviously. It's not a trivial assumption, but we're going to need it to get some results. It's interesting to relax it, obviously. And then I'm going to assume that the priors are common knowledge. Okay, so the principal wants to design a mechanism to maximize his own utility. I'm going to assume no payments, so this is a mechanism design problem without money. And it turns out by taxation principle style arguments, you can restrict yourself to very simple mechanisms. Those are single proposal mechanisms. And again, the proof is by taxation principle. So here, the principal commits to a menu of valuated solutions, I'm going to call them. These are solutions tagged with utilities. And those are the things that the principal considers acceptable. They will include things like, I'll accept this plan if you can attest to me that my utility for it will be at least this much, right? So there's solutions tagged with requirements on the utilities that the principal might want for them. And then the agent adaptively probes some subset of the elements, and then we'll have to suggest a solution from this menu. And the restriction here is that the solution they suggest must agree with the results of their probes. So they have to, because they can't really lie, if they suggest that you take the solution, they can include proof that it satisfies the utility that the principal needs. Jason, you had a question. X's and Y's. X's and Y's. No, X, E, and Y, E may be arbitrarily correlated, but just there's independence across the different E's. That's a good question. I forgot to say that. Any other questions? But however, by the way, it turns out that our policies are not going to depend on knowing anything about Y. So the fact that you can reduce to these mechanisms kind of tells me conceptually that there's essentially two equivalent viewpoints here. One is that you're delegating data collection. Another one is that you're delegating just optimization. You're delegating solving the problem in its entirety. And by taxation principle, those are basically the same thing. Okay. Any questions? So I'm going to study the delegation gap. So this is the loss due to delegation. So obviously, if the principal and the agent have the same utilities, there's going to be no gap, right? But we're going to look at what happens when your agent has arbitrarily different preferences. So we're going to take worst case over agents, and we're going to look at the ratio of the principal's utility when they delegate to their utility if they had the expertise to solve the problem on their own. So some background on delegation. This started with the work of Holmstrom, who obviously did a lot of early work on delegation and contract theory and all that stuff. There's been a lot of work in econ when everything's a real number. And there they mostly characterize the optimal delegation mechanism. So the most relevant model for us is that of Armstrong and Vickers, who delegate selecting one of n options. And the paper that really inspired us is the paper of Kleinberg and Kleinberg on delegated search, where they analyze variants of the Armstrong and Vickers model and reduce bounds on delegation gap to the profit inequality, that classical profit inequality. Okay? So for the rest of the talk, I'm going to break it up into three technical sections. So first, I'm going to look at what happens when you don't have any constraints on your probing set. And then I'm going to look at adding hard probing constraints. These are, you can only probe this many elements or something like that. And then I'm going to look at soft constraints like costs incurred for probing. So now I'm going to make the problem very simple and say there's no probing constraints and there's no probing costs, right? So even here, it turns out the problem is highly non-trivial. Because if you think about it for a second, if your mechanism does nothing and says to the agent, hey, explore as you see fit and suggest a solution, what the agent will do if they have opposite preferences to the principal is they would just propose the principal's ex post worst solution, right? And obviously, that can be arbitrarily bad. Instead, we want to design this single proposal mechanism, which says, here's a menu of solutions and how much utility I want for them, I expect of them. And the agent, knowing that they can only propose things off this menu, what they'll do is they'll probe all the elements in this unconstrained setting, and then propose their own favorite solution that is on the menu and agrees with the results of their probes. So valid means agrees with the results of the data exploration. Okay. So here's the theorem we prove in this setting. If your set system, if your optimization problem constraint is nice enough, then you get constant delegation gaps in fairly general settings. And here, the idea is that we reduce to a strong form of the profit inequality. So in particular, if your set system admits a generalized profit inequality that is quote unquote greedy, and also works against a very powerful adversary who is called the almighty adversary, gets to order things in a really worst case order, then you get the same, the guarantee for the profit inequality becomes your delegation gap. Okay, so if you have an alpha inequality, you get a delegation gap of alpha. And it turns out that such profit inequalities that are shockingly strong were actually shown by Feldman, Svensson, and Zenklusen for basically all our favorite set systems and their intersections, things like matroids, matchings, and knapsacks, and so on. So really, we reduce to their results, essentially. Any questions on the statement of the result here? I'm going to kind of give you an idea of why this is true. So to see why this might be true, I'm going to revisit the result of Kleinberg and Kleinberg for the special case where you want to select one out of n elements, right? Here, the undelegated optimal, your benchmark, is the expected maximum realization of your utilities for these elements. So expected maximum over all elements I of xi. That's kind of the undelegated optimum here. And again, you should start thinking of connections to the profit inequality. You have random variables, and you want to pick the best one, right? So if you think of the profit inequality setting where these random variables arrive online, there's a threshold policy due to Samuel Kahn that guarantees that you recover at least half this benchmark. And it operates as follows. You set a threshold t equal to, for example, the median of the maximum reward, right? So there's a distribution for the maximum reward. You pick its median. And then as these random variables arrive online, you pick the first one that beats this threshold. Okay? And that's shown to extract half of the optimum max IXI. Now, going back to the delegation setting, where instead of these things arriving online, we're delegating to someone to select one of them. What we're going to do is we're going to say to our agent, hey, I'm only going to accept elements that beat this median. Okay? So now someone else is doing the selection for you. You're going to say, I'm going to require that you beat this threshold. And that's the same as designing this menu that I drew here. It's for each element, you tag it with xj's that exceed the median. That's your requirement. If I accept this element, it better beat this threshold. Okay. The key insight, one way to look at the key insight of Kleinberg and Kleinberg is the following. This proof of Samuel Kahn, it turns out, if you look at it carefully, holds even if there's a very strong adversary that looks at your random variables in the profit inequality and gives them to you in an adversarial order. Okay? And what that would do is it would result in you selecting the random variable, the smallest random variable that exceeds the threshold. It turns out that even if that happens, the value of the ratio of half still holds. For those of you who've seen the proof there, if you go back to it, you'd realize that it holds under this very strong adversary, even though it's not clear if you haven't thought of it this way before, right? And if you think about it for a moment, that's the same thing that a worst-case agent would do in the corresponding delegation setting. this agent has opposite preferences to the principal. They have this menu they're constrained to. They would pick the worst principal acceptable solution. So therefore, you would inherit the guarantee of the profit inequality in this setting. Any questions on this? So that's kind of one way to view the result of Kleinberg and Kleinberg. That's the way we view it, and that's the way it generalizes. So let's now move to more general set systems. You're trying to solve a combinatorial problem where you're trying to pick a set S in the set system F, and you want to maximize the sum of your utilities for the elements you select. Let's consider a mechanism that restricts the agent to a menu of downwards closed solutions. What I mean by this is if you accept this set of elements with these utilities, you'd also accept any subset of them with those same utilities. Now, if you think of what a worst-case agent would do, an agent whose preferences are opposite to the principal, is what they would do is they would pick the principal's ex post least favorite solution on the menu, subject to that solution being maximal. Agent's utilities are non-negative, so you'd always pick a maximal set that's on the menu that's as bad as possible for the principal. That's kind of for an arbitrary mechanism with a downwards closed menu. Yes?
Just to make sure I understand, but with downward close, they could just pick very few items, right?
Correct.
So won't they always do that, like pick just one item or something?
Oh, they would always pick a maximal thing on the menu because their utility is non-negative for every element, the agent. So you look at the menu, look at the maximal sets in the menu, and they'd pick the worst one of those. So it's always better for them to pick a one element no matter what than no elements, let's say. Good. So now we can generalize the insight of Kleinberg and Kleinberg. If you look at this mechanism with the worst case agent, it turns out that makes the same choice as a certain kind of profit inequality that's greedy and operating against a very strong adversary. In particular, if you think of a profit inequality algorithm that has this menu R and says, I'm going to accept elements greedily as long as the solution I have in my hand stays in this downwards closed set system R. That's a greedy profit inequality, it's often called. And if you think of how that would behave against a worst case adversary, it would end up picking exactly the thing that this worst case agent would have done. It basically picks a maximal solution that is as bad as possible on this menu. Because the fact that the adversary can order things arbitrarily means it can kind of simulate this very adversarial agent kind of thing. And therefore, if you have such a greedy profit inequality with a guarantee of alpha against this very powerful adversary, then the corresponding single proposal mechanism where you design the menu based on the greedy rule has the same guarantee. And these authors, Feldman, Svensson, and Zenklusen, defined exactly these profit inequalities and proved constant gaps for them for, again, all these set systems. So it turns out that we can reduce to them here. Any questions? So basically, the insight of Kleinberg and Kleinberg viewed this way generalizes. That's not necessarily the way that it was viewed at the beginning, but when you look at it this way, it generalizes to these set systems. Yes?
Are they thresholds or lines?
The menu has, think about it this way. The menu sets, the way you end up needing is the menu that sets a threshold for each element carefully.
Each element given the set?
No, so there's some sets that are good, some sets that are bad. And it's not necessarily, it's a more constrained set system than F. You define a set system, F prime, that is more constrained than F. You set thresholds on the elements there, and then you accept greedily. It turns out there's a way to do this that gets a constant gap. So there's this paper where they take a set system and they define a more restrictive set system and associated thresholds where this guarantee holds. And that's kind of the trick that is needed. But we don't need to open that up. That stuff follows by reduction for us. Okay, so now that's it for the unconstrained setting. Let me now talk about adding probing constraints. By the way, how much time do I have? Okay, that's good. That's good enough. 10 is good. Okay. So now, let me now talk about what happens when your probing is not for free, right? So one way to capture that is through hard probing constraints. That's the easier one to handle, so I'm going to talk about it first, and that's our first paper. So now, in addition to the set system F of solutions, we now have another set system G, which tells us which sets of elements we can probe. So you can pick a set P that's feasible in G to explore. So for example, in our transit network example, maybe you can explore at most K designs. That would be a uniform metroid constraint. Or maybe you have at most a certain amount of time to explore the possible designs, and each design takes a different time, so you have a knapsack constraint, and so on and so forth. Right? Now, if you think of the undelegated problem here, this fits into the literature on what's known as stochastic probing, or stochastic multi-value probing, which has been studied, and we know a lot of things about it. So in particular, this is stochastic probing with adaptivity when you have inner constraints F and outer constraints G. Inner means the things you're about to select. Outer means the things you're allowed to probe. Okay. So usually, obviously, the outer constraint is generally more permissive than the inner constraint. Okay. Now, our benchmark, which is the optimum in the undelegated setting, is more intricate. It's harder to characterize in this case because it really depends on, it really asks what is the optimal data to explore so that you can select a subset of it that's good, right? So that benchmark is a little trickier to pin down. So that means morally that it's hard to use profit inequalities in a kind of a direct way. So we need an additional idea. And the challenge, I like to think of it this way. How can you, as a principal, incentivize a good data exploration strategy, a good probing strategy, in particular, an adaptive one? That seems very difficult because you don't see the sample path of the agent. You never end up seeing the variables they probed that they didn't end up proposing. So there's no way to enforce, hey, if you see this, go that way, or if you see that, go this way. Because you never get to see that information, you don't see the sample path, so it's difficult to see how you can incentivize any good exploration strategy here. It turns out we can just get around this issue. Forget about adaptivity, just settle for non-adaptive policies, and it turns out that that's enough in shockingly general settings, and we'll see why that is. Again, we're just reducing to stuff that's already known by looking at the problem the right way. So for these kinds of stochastic probing problems, you can often define a notion called adaptivity gap, which is the ratio of the best non-adaptive probing algorithm to the best adaptive algorithm. And the non-adaptive probing algorithm just picks the set of random variables to explore up front without seeing any data. Okay? So there's an offline choice of the stuff to probe. So here's a theorem from our first paper on this. If the stochastic probing problem has adaptivity gap alpha, then we can reduce the constrained probing setting to the unconstrained probing setting at a loss of alpha. And that's kind of, the proof is exactly what you'd hope it would be. Just tell the agent what to probe. In particular, tell them you're only allowed to probe this non-adaptively approximately optimal set, capital P, and I'm going to only accept those elements. So, you're basically constraining the agent to probe this best non-adaptive set. So you lose a factor of alpha up front, and then you can do the profit inequality trick we did before. Okay? So the two things compose in the nice way that we'd hope. So, it turns out there's this very general adaptivity gap result. In fact, a ratio of 2 for very shockingly general settings. This is Braddock, Singla, and Zuzek, I believe. And basically, they show adaptivity gaps that are 2 for any downwards closed probing constraint, as long as your problem you're solving underneath involves a constant number of matroids. So here's our corollary from that result. We have a constant delegation gap for any downwards closed probing constraint, and any solution constraints that's the intersection of a constant number of matroids. We don't know what happens for things like knapsacks yet, although we didn't think about it very hard. It's interesting to see how you can push this. I would bet you can push it for more variety of different things, but we didn't really try. Okay, so that's it for the hard probing constraints. Let me now look at soft probing constraints, where you have costs for probing different random variables. So for each element E, there's a known cost C sub E for probing it. Now, if you think of the undelegated version of the problem here, this is just a generalized Pandora's box problem. Some of you may be familiar with the classical Pandora problem, where you're trying to pick one of n options. This is a generalization where you can pick a subset of the options subject to constraints. And you know, these kind of generalizations have been studied, starting with the work of Singla, and Brendan had some interesting work on there as well. We're gonna use. So this kind of stuff has been studied. It's very interesting. Okay. Now, when you think of delegating this thing, now there's a subtlety about how you model the exploration costs and who bears them. And it turns out we need to look at different models because the possibility terrain here is a little less clean. So we look at 3 models. One model, we call it something different in the paper. Here I'm going to call it split cost, where the principal and agent pay equally, or according to a fixed percentage, like the principal always pays 20%, agent 80%, or something like that, in terms of probing costs, right? Then there's the free agent model, where the principal just bears the entire cost of exploration as part of the contract. Hey, whatever you explore, I'm just gonna foot the bill. And then there's the most permissive model, it turns out, is where the principal, as part of their mechanism, they get to stipulate what percentage of each element's probing cost they're going to pay. So they can say, hey, this option seems very promising. We're going to foot the bill for you to explore it. But this other option seems like high risk, high reward. So if you're going to explore it, to do it on your own dime, I'll pay maybe like 10% of that or something. So you can do things like that in this mechanism. Now, if you think of what happens when the principal delegates a menu of options, and that's really all the principal can do, as we all described, what happens is that the agent solves the Pandora problem constrained to that menu, but using their own utilities instead of the principal's. And I want to set up that menu in a way that the principal can guarantee that they recover something good. Okay. So there's some indications that we might be able to use a similar reduction to profit inequalities approach here. And that comes from the beautiful work of Esfandiari, Hajagai, Brendan, and Mittenmacher, right? Where they basically reduce these generalized Pandora's box problems to profit inequalities of a certain form. And it turns out that the form of profit inequalities they reduced to are exactly the form that we needed in our earlier reduction. So things should work out. Yes?
A key thing about the previous model without cost is the principal couldn't tell which things the agent wrote.
Yeah.
And I didn't really understand how that would still be the case with your cost models.
Would it help if I say that the principal cares about the social cost of exploration?
The principal cares about the cost, but doesn't maybe observe the cost.
Yeah.
Got it.
Yeah.
Thank you.
Okay. It's a very good question, actually. Okay, so this paper tells us that we might be able to reduce to the profit inequality, use that to derive a menu, and hopefully things will work out. We were hoping that. It turns out that that's not true. And I'm going to have one slide for those of you who are familiar with the Pandora's box type problems, and tell you what the problem is, what the difficulty here is. So Pandora's box type algorithms, usually what they do is they look at each element's reward distribution and split it into 2 parts. I'm going to call them the head in green here and the tail in red. Okay. And the red part, the tail, is calibrated just so that its expected value exactly covers the cost of probing the element. So the tail pays for exploration. The head is the bonus you get on top of that. That's kind of the additional utility you get beyond exploration. Okay. So in all those algorithms, usually what is the property that's needed is what's known as non-exposure. If you probe an element, E, and you find out that its value is in the tail, you better select it because the tail has to pay for the cost of exploration. So if your value happens to be in the red part, you better pick that element if you probed it. That's called non-exposure. Okay? And by the way, this threshold between the head and the tail is often known as the strike price or reservation price or cap value, I think. So there's a bunch of different ways that's known. Right? Now, the reduction of this nice paper to profit inequalities guarantees non-exposure, as is often required to get results. And alpha approximates the green contribution. So that's how it gets the alpha approximation. Now, we could use that to derive a menu, the way we've talked about before, and see what happens. And we tried that. And it turns out that preserves the green contribution, but that breaks the non-exposure. So now the agent may sometimes probe something, find out it's in the tail, and say, hey, you know what? Even though I probed it, I'm not going to select it. I'm going to go for something else that is, because my utilities are very different than the principals, I'm going to go for something else that I'm going to select instead. So this reduction breaks non-exposure. This is an obstacle. It turns out to be insurmountable in some settings, surmountable in others through additional tricks. What we do is we do a bunch of work and reduce this problem in some cases to the strong contention resolution schemes of Feldman, Svensson, and Klusin, and we get this menu of results for our various models. In the split cost setting, we get fairly nice general results for the distributions that are binary. Beyond binary distributions, we show nothing non-trivial is possible. And then for the free agent setting and custom cost setting, we get fairly nice positive results in many settings. For one of them, we need to have a by criteria guarantee of discounting the cost, but that's kind of a technical condition. Right? So the details of that, I'm not going to steal my students' thunder. The details of this result are going to be at EC. There's a lot of technical details here. So I'm going to close with some open problems. Our bounds are very loose. They're just through these reductions. The reductions aren't reversible. We didn't look at computational complexity of the optimal policy here. You could forget about comparing to the undelegated optimal and say, what's the optimal policy? How do you compute it? The most interesting question that I think we left completely open is similar to something that John mentioned earlier. It has to do with randomization. Do randomized delegation policies help here? We started exploring this in our papers. We have mixed results. They seem to suggest that it helps in some cases, but not in the worst case, but we really haven't proved anything. And I think that's an interesting avenue for future work. And that's all I have.
Thank you. Do you expect these results to change a lot if you restrict the agent to having preferences that are not too far from the preference of the principal?
Yes. If the agent has similar preferences, then that approximation carries through to the principal with a kind of trivial policy. It depends on exactly how you define the goals.
Okay, I see. Because what struck me during the talk, I'm very a beginner in this field, is that having the agent with completely opposed preference is a bit unrealistic.
Yes.
So, okay. So that.
That's right. So the tricky part here is that if you assume that they have the same preferences, the problem is trivial. There's nothing
Yeah, sure.
to do, right? What we're trying to do is we're trying to say, what can you guarantee no matter what? If you had a nice metric of defining how different those preferences are, that would translate to kind of easier to get kind of delegation policy that would preserve that approximation. How to define that metric in a way that's interesting but not trivial is kind of not something we try to do.
Okay, and there have been no atoms so far.
Sorry?
There have been no attempts so far.
Not that I'm aware of in this particular setting.
Okay, thank you.
Yeah, I'm not sure. Sorry? Independent?
XE and YE being independent preferences.
Yeah, actually, so the Climber paper had that as one of their models. We didn't look at that, but they have improved results in that such a case. I would imagine the same will carry over up to a constant, honestly.
But we're clearly working basically age and go and explore whatever you want.
I don't think so.
Thanks again.
Yeah.
So last up, we'll have Sam Taggart, who will be joining us remotely.
Should I share my slides?
Yeah, we can hear you. I think you can show your slides now. Yeah.
All right.
Okay,
Behold.
yeah, it's up.
Cool.
Great, thanks. So Sam will be telling us about simple delegated choice.
Okay, cool. Can you hear me okay? Yes?
Yeah.
Good, okay. So thanks for the introduction, Brendan, and thanks for putting together this fantastic workshop. I'm sorry I can't be there in person, but I'm feeling a little under the weather. So I am literally giving this talk from a hotel room 1 block down the street. I'll try to keep the weird sniffling noises to a minimum. So actually, Brendan, when should I end? Since we're behind schedule.
Oh, lunch doesn't actually start until 12:15, so you can have the 35 minutes. So maybe end at like 12:05.
All right. Cool. Sounds good. Okay, so this is joint work with Ali Kodabash, who was a grad student at UT Austin at the time, and Manolis Punarakis, who is faculty at Drexel. And so I'm going to be talking about a canonical model in microeconomic theory that until very recently hasn't seen any attention from TCS. So this is going to be very similar to what Shaddin showed you, but we'll deviate in a few pretty key ways. So I'm going to build from the basic ingredients. So this is a principal agent problem. So we have a principal who has some action that they need to take, and they need to pick which action to take. But the choice of which action is correct is going to depend on some state of the world, which the principal can't observe, but there's some agent who can observe this state of the world. So let me give you a couple of like touchstone examples. You could think about a firm that needs to replace some new fancy piece of equipment. This piece of equipment maybe is going to be used by some specialist. So the firm doesn't really know which of these brands of this equipment is good, but the specialist does. So the firm has the authority to like pick what gets bought, but it's really the specialist who has all of the knowledge of what's good and what's not. So you should think about the action as being the purchase choice and the state of the world being the qualities of the different brands of this piece of equipment. Another timely example for me is when I teach advanced algorithms, I require the students to read a paper and write a project about it. So I'm the principal, the students are the agents, and they need to pick their projects, but I have the authority to tell them what to do and not do. But I do care that they work on something that they like. So there is some unknown state of the world, which is their preferences for the different topics in their TCS paper. Okay, so 2 key pieces here are that preferences for both the agent and the principal are state dependent, right? So the firm wants to buy the best piece of equipment. The specialist also cares that the equipment is good because they're going to be the ones using it. But these preferences are possibly misaligned partially. So in the purchasing example, both the firm and the specialist care about quality, but the firm is the one footing the bill. And so there's a misalignment with those prices. So this is a general setting for mechanism design. You could imagine mechanisms that have a bunch of communication or randomization. But if you have a deterministic mechanism, it's without loss of generality to consider mechanisms where the principal just delegates the choice. So they give a menu of allowable options and let the agent pick their favorite after they observe the state. So other than the stuff Shaddin just talked about, the canonical citations in the microtheory literature are these 2 papers, Melamad and Shabano and Alonso and Matuszek. And they characterize a single variable version of the delegation problem. So actions are just numbers between 0 and 1, as are states. And you should think about the state as being like the recommended correct action. And they consider single peak preferences, or in particular like quadratic loss preferences, where both the agent and principal have some bias that nudges their preferred action one way or the other. And the like classic result in this area is that the optimal mechanism is an interval. So the principal says you're allowed to choose from here to here, pick your favorite. So we can reflect on these papers and in the light of our examples and ask ourselves, does this model really line up with the stories we are telling ourselves about delegation? So is it possible to take the space of equipment choices and put them on an interval? Maybe not. And I certainly hope it's not possible to do that with like theoretical computer science papers. Hopefully that space is much more rich. So really the problem here is that a lot of these interesting delegation scenarios that you might want to think about are discrete choice problems where this single variable model really doesn't capture everything. So that's the goal of this work, is to write down a nice model for delegated discrete choice. And we analyze the power of simple mechanisms in this model, in 3 different versions of this model, and we give tight characterizations in each. So I'm going to spend a bunch of time today talking about the model itself, because I think it's interesting. And there are a lot of interesting comparisons to be made to other work. And then I'm going to give you a sense of the kind of key economic intuitions driving what I think of as one of our main results, which is a 3 approximation under an independence assumption. And then I'll maybe sketch one of our other results if I have time. Okay, so let's get to the model. We're thinking about discrete choice. So we have n actions that we have to choose from. Each action is going to have a utility for the principal and a utility for the agent. And I'm going to assume that utilities are the following form. So the principal's utility is for action I is going to be some number vi. And the agent's utility is going to be vi plus some bias term, which I'll say is bi. So vi represents the part of the utilities that are aligned. Bi represents the part of the utilities that are misaligned. So this gets to one of the questions that was asked after Shaddin's talk. So I'm going to assume that the principal's utilities are non-negative so that we can do approximation. And I'm going to assume that these values, the VIs, are the part of this problem that's unknown. So you should think about the vector of the VIs, one VI for each action you could take. That vector is the unknown state that the agent observes. Now, crucially, we're going to assume that the biases are known and fixed in advance. And this seems like a strong assumption because it is. But I claim that it captures the intuition of many of these scenarios that we talked about. So for example, with the equipment purchasing example, the thing that's unknown is the quality of the different equipments. The thing that's known is the different prices. So you might write down the utilities of the principal and agent in the following way. The principal's interested in quality minus price, the agent's interested in quality. But if you rewrite the agent's utility as quality minus price plus price, then there's a shared uncertain value term and a known bias term, because we can assume that the firm knows the prices of the different pieces of equipment. Okay, so that's the utility model. Again, the timing of this game is going to be the principal presents a subset of actions that they're going to allow the agent to pick from. The agent is going to observe the state, which is this vector of values, and then they'll pick their favorite, which is the one in the delegation set that maximizes value plus bias. Okay, so this would be a great time for one question about the model before I move on.
Looks like no questions.
Okay, great. So the principal's goal is to maximize their value that they get from the thing that the agent chooses. So if the agent chooses I star, they want to maximize their expected value from I star in expectation over the unknown values and the thing that the agent chooses. Okay, so it's worth taking a moment to compare ourselves to the stuff Shaddin just showed you. So there's this line of work, I forgot to cite Armstrong and Vickers, that's also in this line of work, where they study what I think about as the delegated search problem, whereas this work is really about delegated choice, our work. So what do I mean by that? Well, as Shaddin showed you, he thinks about a model where the information isn't necessarily known to the agent. They may have to solve a search problem like a Pandora's box problem to obtain the information before they make their choices from the principal's menu. We're not assuming that that never happens. So the agent observes all of the values perfectly every time. So really, we're trying to just capture the problem of choice and not of search. There's one other really key distinction between our model and the Kleinberg et al. Models, which is we're assuming that only the identity of the action chosen and therefore the known bias is observable. This is different from the Kleinberg et al. Models, where they assume that the action chosen has a verifiable principal utility. So the principal is allowed to specify contracts like, get me X utility or more, or I'm going to leave and go home. We're not allowing the principal to do that. They just say, here are the actions you're allowed to take. I'm not going to observe my utility for that action just yet, until after you make the decision. Okay. It turns out that this latter distinction actually makes a huge difference. So in the Kleinberg et al. And follow-ups, they're able to use profit inequalities to obtain an approximation to the first best principal utility. So this is the utility of the principal if they just solved the search problem themselves, which is really cool, but it turns out you can't do that in our setting. You can show that there are examples where the principal just can't approximate the first best to any factor better than like n. So somehow this ability to verify is really powerful, and we're not going to give ourselves that power. And because we can't approximate the first best, we're not going to ask about comparisons to first best. We're going to study comparisons to the optimal delegation set, or the second best solution. So we have a different benchmark because our model affords us really different things. Okay, so there's one other line of work that's really important to compare to, which is the literature on assortment optimization. The canonical citation is probably this paper of Telluri and Van Ryzen in management science, but this is a really, really deep literature. The story in assortment optimization is that there's a seller who offers fixed price items to a buyer, so they're picking the inventory for their store. And if you write down the utility model for assortment optimization, it actually looks quite a lot like ours. So the seller has some revenue that they get when item I is purchased, and the buyer has some unknown value that gives them utility value minus price when they purchase item I. The big difference is that this revenue is fixed and known to the seller, and it's the buyer's value that is unknown. So this actually isn't quite our model, right? Because we had the values shared before. But if you massage this a little bit, take some really small epsilon and rewrite the utilities like this, you can still get it so that there's a shared unknown value term in both people's utilities, and there's a known bias term that's fixed in the buyer's utility. And the buyer in this model with this epsilon here is going to behave exactly like they would in the model at the top. So this almost shows that we can capture all of utility-based assortment optimization in this model I just showed you. We're not quite there yet, though, because usually in the assortment optimization literature, it's standard to assume that the buyer can walk away. They can either choose not to purchase, in which case the seller gets zero utility and the buyer gets zero utility, or maybe they go and purchase somewhere else, in which case the seller gets zero utility and the buyer gets some positive utility. And the big distinction is that this no purchase option, action 0, the outside option, is always available to the buyer, no matter what set the principal chooses. So we're going to give ourselves the power to capture all of this by giving ourselves an action 0 as well, an outside option. So we'll assume that there is an action 0. You have to include action 0. And notice that this is strictly more general than the model I just showed you before. So if you wanted, you could make the bias of action 0 minus infinity, in which case the agent would just ignore it completely. But now we can also capture all of utility-based assortment optimization. Okay, cool. So what are simple mechanisms in our setting? Well, we're going to analyze threshold mechanisms. What a threshold mechanism does is it tells the agent, okay, you're allowed to pick any action you want as long as its bias is at most some threshold t. Or you can pick the outside option. These mechanisms are practically ubiquitous. So in our equipment purchase example, this is just the firm imposing a budget on the specialist. In assortment optimization, these are really well-studied objects. They're usually referred to as revenue-ordered assortments in this literature. So we're going to be analyzing how well threshold mechanisms do compared to the optimal delegation mechanism. So in some sense, you can think about this as explaining their prevalence. And we do so under 3 sets of assumptions on our unknown value distributions. So the first is we assume that the values are totally independent. And we assume our outside option has a fixed value. So that's like, don't purchase in the assortment optimization example. And we show that threshold mechanisms are a 3 approximation to the optimal mechanism. If you relax the fixed outside option assumption and put the values between 0 and 1, we give a multiplicative additive bicriteria approximation. That's a mouthful, but basically what we're saying is either you can additively epsilon approximate opt, or you can multiplicatively log over log log 1 over epsilon approximate opt. So either you're guaranteed a good multiplicative or a good additive approximation. And then finally, we give a general analysis for arbitrarily correlated VIs. Here, P min is the probability of the least likely value vector in this correlated distribution. And all 3 of these sets of results are tight. I'm going to show you the first 2. In particular, I think there's some really cool intuitions, economic intuitions for the first result, and then maybe I'll talk a little bit about the second ones. So here's the first result stated formally. The game plan for proving this result will be the really 2 big steps. So step 1, we're going to take the utility from the optimal delegation set and decompose it. So you can think about the task of the optimal mechanism as having 2 parts. Subtask 1, if there are really high values, you would love to give the agent the power to choose these really high values because you like those high values too. On the other hand, if there are no really high values and there are only maybe medium values, then you need to be a little bit more careful. You need to make sure that the agent doesn't get distracted by something that has high bias but low value. So we're going to decompose the utility into 2 terms that represent each of these cases, basically. So we'll have a term which I'll call sur or surplus, which will represent this aligned value when the values are high and both the principal and agent are happy. And since this is really the term where preferences are aligned, you might expect that this is going to be pretty easy to approximate, and it turns out to be so. And then we'll have this other term, bias difference is what I'll call it, or BDiff, which represents this sort of misaligned utility case where the principal really has to control what the agent does. And this is going to be a little bit harder to approximate. So that'll be the second big step in our proof. Okay, so from now on, I'm going to assume that action 0 doesn't exist. The analysis isn't going to get much more interesting if we do introduce it. Remember, it has fixed value for this result. Okay, but before we jump into the analysis, it turns out that there are some really nice pictures you can draw that help understand what's going on in the utility from an optimal solution. So the thought experiment I want you to imagine doing is draw a vector of values, figure out what the agent would pick, and plot the bias of that action against the value from that action in that realization. And just do this for every realization of the values, so you have a point for every time the agent chooses something in opt. You'll get a picture that maybe looks something like this. One thing that you might notice from this picture is that I've drawn these points in columns. The actions have fixed bias, so each action is going to have a column corresponding to all of the realizations where the agent picks that action in opt, all of the different values that it can take in those realizations. Okay, so the nice thing about this picture is that it also allows us to visualize the preferences of the agent and the principal. So the agent or the principal is interested in value, so they want the points to be high. The agent is interested in value plus bias, so they like points that go to the northeast. That's the direction of improvement for them. Does this picture make sense? I want to take a second to make sure there are no questions about it.
Questions? Lots of thumbs up, no questions.
All right. I appreciate the feedback. Okay, so one other thing you may have noticed about this picture is that there are no points in this triangle in the bottom right. And this is for a reason. So I've drawn this triangle anchored in its bottom right at the highest bias action in the optimal solution, B4, or action 4. And notice that everything in this triangle is dominated for the agent by every single realization from action 4. The agent will always choose action 4 over any point in this triangle. And so there's always going to be a triangle like this where you have no realizations in opt. And it turns out this triangle is really the key to obtaining this decomposition I told you about. So I've isolated one point And I want to think about that point's position relative to the triangle. So the triangle is anchored at the bias of the highest bias action in opt. Let's call that bias Bmax. Then the upper edge of the triangle has formula Bmax minus Bi. The principal's utility for this point, this realization in opt, is going to be Vi star, but you could add and subtract this bias difference Bmax minus Bi star if you wanted. And this gives you two terms. The first term, value minus the bias difference, that's what I'm going to call the surplus of action I star. And visually, it's the distance from the dot to the top of the triangle. What I'm going to call Bdef is this difference in biases. So it's going to be the distance from the top of the triangle down to the x-axis. And that's going to be our decomposition. So take the expected value of the thing opt gets and decompose it into its surplus quantity and its bias difference quantity. Now, it might not be obvious to you yet that surplus represents the aligned part of the optimal utility and bias difference represents the unaligned part. So let me try and convince you by showing that surplus is really easy to approximate. So in particular, you can tell the agent, pick whatever you want, but don't pick anything that has higher bias than the most biased action in opt. This is sort of the grand threshold, the threshold that is the smallest threshold that includes everything in opt. And if you do this, it turns out you are guaranteed to get this surplus term as your value. So you're sort of letting the agent do what they want. So here's why that works. They're going to choose, the agent's going to choose something from the grand threshold. Let's call that I star or I hat. If they like I hat better than the thing that they chose under that same realization in opt, then you can just write down the inequality. Their utility from I hat is higher than their utility from I star. The utility from I hat is at most the bias in I hat is at most the max bias in anything in opt, just by definition of the threshold. And like you can just rearrange this and take expectations. So somehow this surplus term really is the portion of the utility that the agent and the principal agree on. And you can just let the agent do what they want and they'll basically give it to you. So that gives us a one approximation of the surplus term. Now let's think about the bias difference term. And this is going to be much trickier. So to understand what can go wrong, let's imagine that we are, again, offering this grand threshold. And let's see what could sabotage us. Well, we're allowing lots of actions that have high bias. And so one thing that could happen is that there could be an action with really high bias that the agent really likes. And in this picture, that's the blue point here. So the agent's going to take this really high bias point over any of those pink realizations from opt, which is too bad because those pink realizations are much higher up. They give us much more utility for the principal. So if you allow really high bias actions, you might have this problem that you distract the agent. Now, to compensate for this, you might imagine setting a really, really low threshold, but that can also go wrong. So these the points in the picture are just the realizations that the agent actually took in opt. So if we allow ourselves just action one, like I've done in this picture, we know what action one looks like when the agent takes it, but we don't know what it looks like when the agent doesn't take it. And in particular, action one could be really terrible in every other realization. We could have maybe zero utility. And if that's the case, then we just threw away like all of these actions for just action one, which turned out not to be very good. So the problem here is that this threshold can also exclude too much from the solution. Okay, so here are two problems. What I want to do is just write down some conditions that basically just say problem one doesn't happen too much and problem two doesn't happen too much. So I'm going to define a threshold to be alpha guarded if problem one doesn't happen too much. So in particular, it's going to be alpha guarded if you look at Bmax minus the threshold, and that's high. Or in other words, the threshold itself is pretty low. And in particular, the right-hand side is an alpha fraction of this Bdiff term that we're trying to approximate, the bias difference in opt. So literally all this is saying is that T is high, and how high? Well, it's governed by alpha. Okay, so that's problem 1 can't happen very much. To write down a condition for problem 2 not happening very much, well, let's just look directly at the pictures. So we saw that we were very unhappy when we cut off lots of these pink points. These were the realizations in opt. So let's just look at all of the opt realizations that are still from actions that are inside our threshold set. So that's these 3 points for action 1 and the 2 points for action 2. And let's just write down a condition that says that those represent a lot of utility. So in particular, we'll define a threshold to be beta inclusive if the principal's utility from those points from opt that are still included in our threshold set represent at least a beta fraction of our bdiff term. Okay, so we've just got 2 definitions to say problem 1 can't happen very much, problem 2 can't happen very much. The cool thing is, these are really the only 2 problems that can happen. So you can show that if you have a threshold that happens to be alpha guarded and beta inclusive, then it's actually going to do a really good job of securing you a good fraction of bdiff. In particular, it'll secure you the minimum of alpha and beta. And the reasoning is not too bad. I won't give it to you precisely, but I can give you the intuition. So let's look at the thing that the agent chose, or rather, let's look at the agent's favorite thing from the threshold set that isn't also in opt. So this is like their favorite new action. If they don't like that favorite new action very much, then they're going to pick something that they would have picked in opt. Great. Our threshold is beta inclusive, so there's lots of good stuff for them to pick from. On the other hand, if their favorite new action is really appealing to them, well, we set up our threshold so that that new action can't have very high bias. So the reason the agent must like it is because it has pretty high value. And if you write down the inequalities, you can actually show that you will indeed get a lot of value from that other case. So if you have something that's alpha guarded and beta inclusive, you're guaranteed a good fraction of the bias difference term in our decomposition. So you might then ask, well, is this reasonable to ask for? Are there actually thresholds that are alpha guarded and beta inclusive? And the answer is yes. So here's one threshold you could use. Start at Bmax and shade towards lower thresholds. And how much should you shade? Well, just shade bdiff over 2. That turns out to be half guarded and half inclusive. Now, if you've worked with profit inequalities, you might be getting chills or something because, well, this alpha guarded condition really looks a lot like the revenue term in the original Samuel Kahn profit inequalities analysis. And this beta inclusive condition looks a whole lot like the utility term in the profit inequalities analysis. And actually, setting a threshold related to half of the thing you're trying to approximate is also very similar to the profit inequalities analysis. And if you do this really carefully, you can do a version of this analysis just using basically the same arguments from Samuel Kahn. The nice thing is that these definitions then allow us to prove some other theorems that I stated earlier, not just this 3 approximation result. Okay, so let's put all of the pieces together. We have approximated surplus. We've 1 approximated it with the grand threshold. We've 2 approximated the bias difference term using this careful, guarded, inclusive threshold. And if you look at those, that gives you a 3 approximation. The last thing to note is that if you had an outside option that was not just trivial, this analysis doesn't really change. You could just use a different number for Bmax, basically, and that's the only difference you need to make in the analysis. Okay. So that's the 3 approximation result. I basically gave you the full proof. You could like write down a little bit more math and you would have literally the stuff written in the paper. Let me talk to you now about what goes wrong when you have a random outside option. So this is the case where we capture all of assortment optimization. So this is a really interesting case. You can think about the process of the agent choosing as going the following way. They pick their favorite inside action, their favorite action that isn't action 0. And then they realize the value for action 0 and decide if they want to switch. So really, it's like the same decision that they had to make before, but now something could go wrong at the very end. And now we can ask ourselves, in the 3 approximation proof, what breaks now? And one thing to remember is that we got our utility in this 3 approximation proof from 2 main places. The first place was we relied heavily on some realizations where we got the same thing that opt was getting. That was the whole purpose of this inclusiveness property. And that's going to still work fine. If the agent picks something from opt and that thing survives the outside option, then it'll survive the outside option when we try to pick it in our threshold set as well. The real problem, though, comes from the other case. So we're trying to get utility from low bias, high value actions that are not the same as the actions we were taking in opt. And the problem here is that we can no longer really predict these new actions from our threshold set, whether they'll survive the outside option or not. It's just hard to predict. And in fact, it's so hard to predict that you can actually set things up where now with this randomized outside option, the best threshold is at most a trivial N approximation. So that's a bummer. So that's why we need this by criteria analysis. So here I've formally stated it. So again, we're assuming the values are independent. We're assuming the values are all between 0 and 1. And now the statement is pick any epsilon you want. Either I'm able to additively epsilon approximate opt with a threshold, or I can multiplicatively log over log 1 over epsilon approximate opt, again, using the best threshold. So another way of saying this is either you can get a good multiplicative approximation or opt is going to end up being very, very small, as it turns out. So I'm not going to prove this, but instead I'll just give you sort of the proof sketch. And it uses some of these ideas of guarded and inclusive thresholds again. So rather than thinking about one guarded and inclusive threshold, we're going to think about a sequence of these guarded and inclusive thresholds and try and like pin down what is happening across opt's different sources of value. So if one of these thresholds happen to give us good approximation, then we're done. But if none of these thresholds give us good utility, then something fishy has to be going on. In particular, if none of our thresholds are a good approximation to opt, then it must be that this outside option really is causing us a lot of problems. And the rough idea you should have is that this is also going to cause opt a lot of problems. And so opt is going to end up being very small if all of our different thresholds fail. Okay, so that's where I want to wrap up. So again, the big takeaways from this paper are, I think we present a really nice model for delegated choice that walks this line between having things perfectly aligned with the principle and totally unaligned with the principle. And it turns out you can do lots of really interesting things in this model. And we give simple versus optimal analyses for like 3, I think, very natural versions of this model. So I think of these as pretty economically meaningful results. There's also this last theorem that I just want to mention again. Again, I'm not going to get into it because I think the proof is less interesting than the stuff I showed you. But more broadly, hopefully this session has convinced you that delegation is a really cool core microeconomic problem that like really computer scientists should be studying more. There's a lot of really great questions here. So in our particular model, 2 sets of questions you could think about are, rather than having this fixed bias term, what if it was random in some way? Or what if the value and the bias were correlated in some way to each other? There's a whole bunch of slightly more general models than the stuff I presented to you that like I have no idea about and I think are really cool to study and capture some really meaningful settings. Another thing you could think about is, rather than simple versus optimal mechanisms, why not just think about optimal mechanisms? How hard is this to compute? We don't have a lot of good ideas here either, but I think it's a really important and interesting question. Cool, so that's where I'll stop. Thanks for your attention.
Great, thanks so much. A couple minutes for questions. So actually, I have one. When I think about delegation, I mean, one thing I think about also is things like putting out requests for proposals and trying to leverage getting recommendations from like more than one agent. And I guess I wonder if there's like if that sort of line of work, see, like if I could do things like, oh, I'll have people compete on how low a bias they have or something like this. Is this something that's been explored?
Probably in the econ literature. I don't know. When you get into multi-agent bias, things get a little fussier, as you might expect. And I think, yeah, I just don't know my way around that particular part of the literature very well. But like, it's a very natural question to think about. So like, I would be very surprised if economists hadn't thought about it. Yeah, but I don't have like a citation for you.
Okay, great, thanks.
In your approximation bounds, I actually, could you remind me what epsilon was?
So, oh, let me just go back to so you mean in this one?
Yes.
Okay, so here's the
Any
game you play.
epsilon.
Someone gives you an epsilon. They say, here's how close I want you to approximate opt. So either you are going to be able to additively approximate opt to that. So the epsilon is just something that someone gives you. And for any epsilon you choose, this statement is going to be true. Either you can get a close additive, you can get like an additive epsilon approximation, or you can get a multiplicative approximation that is a function of epsilon, but unfortunately it's not like, oh no, it's way better than linear. It's log over log log.
And as I make epsilon smaller, then the mechanism gets more complicated?
No, so this holds for all epsilon simultaneously for the best threshold. So like if you take epsilon really small, the additive approximation binds hard and the multiplicative approximation binds like barely not at all. And as you take epsilon really big, then the additive approximation is useless and the multiplicative approximation starts binding really hard. And so the point is at least one of these is always going to be useful to you.
There might be a typo on the slide.
There may be a typo.
Log over log sounds like both of them are getting better in epsilon, but I think it's supposed to be the reciprocal of that.
It may need to be the reciprocal. Well, so wait, log over log is a number less than 1, right? So I think we're greater than a number less than 1, and that number less than 1.
This is good.
Okay.
Yeah, I think this is right.
So the left bound gets better, the right bound gets worse.
Yeah, and that's the point.
And I actually, when you were talking, I thought you were saying that when the additive bound is trivial, is it the case that, is it just that we get the bound on the right, the multiplicative bound, or opt is less than epsilon? Because then the right-hand bound is trivial in that case, right? If opt is less than epsilon, then APX bigger than opt minus epsilon doesn't tell you anything interesting. And
If opt, well, so opt is less than, like the point is that like the way we get the additive approximation is when opt is less than epsilon. So the point is that like, because we're bounding the values on 0, 1.
But just, I don't really care about getting at least opt minus epsilon when opt is less than epsilon.
Yeah, I mean,
And so writing that as an additive approximation seems a little strange.
Okay, I mean,
Instead, I could just say,
here's another way you could write it if you'd prefer. I mean, the way I wrote it is true, but if you prefer, you could write it this way, which is either you get a good multiplicative approximation, or opt is really small, and so you can think about this as saying that opt has to use really, really extreme values very, very infrequently, and so somehow this is like the only time you're not going to get a good additive or good multiplicative approximation is when the instance is like really messed up.
Great, thanks.
Still a question about the approximation. Can you, if you tune the epsilon, choose it carefully, get only a multiplicative approximation?
So if you tune it really, I don't think you can just get a multiplicative approximation because I can drive opt to 0 and like ruin your approximation. I guess if you had values bounded between like delta and 1, then maybe.
But okay, what happens if I just choose epsilon to be opt over 2?
If you choose epsilon to be opt over 2, okay, yeah, fair. I mean, I don't know what the multiplicative approximation you're going to get out of that is. Because I don't know what log over opt over 2 is, but like, sure.
All right.
Yeah, you're asking me like hard math questions. I don't like this.
All right. Oh, one more.
You're supposed to be nice.
I mean,
and say,
it sounds like from this combination of bounds is that you maybe really want to express your approximation as a function of opt.
yeah, you could do that. That would be fair. Yeah, that's a good observation. Thanks.
Great. All right, let's thank Sam again.
Cool. Thank you.
All right. And with that, our workshop on optimizing the effort of others comes to a close. I hope you're all as excited about this as I am. The point of the workshop, like our goal coming in, was to take these different areas that are based around incentivizing effort and find connections between them and connections into like other areas that have been really well studied in Econ CS. And I think really like all of our speakers really hit it out of the park on like bringing this forward, right? So we saw connections between contracts and scoring rules, and contracts and incentive-aware learning, and scoring rules and Bayesian mechanism design, and delegation and stochastic optimization, and like I hope you take away there's just a really rich space here, and like tons of open questions that we really should be thinking more about, and can really drive a lot of really interesting work. Sort of covers more of economics and classic economic theory we've been doing so far. So I really want to thank all the speakers, and I also want to thank all the participants for the really great discussion, and my co-organizer, Michal Feldman, who unfortunately had to leave early, is not here right now. So yeah, no, thank you for everyone who was participating. And with that, let's go to lunch. Goodbye, everybody.